Hello, my name is Elaine, and today I will be talking to you about supernovas. We will also be discussing the importance of supernova to our astronomers as well as our scientists. I will give you a step-by-step look through pictures the birth of a type 1 supernova. Now, first of all, you, I'm sure, have heard of supernovas, but you may not know some of the details about why these things occur in our universe. Let me start by saying a supernova is an exploding star. It is when the star has reached its life cycle and it basically explodes. Now, there are two types of supernova. And there's a type 1 and a type 2 supernova. But because of time restraints, we're just going to simply talk about the supernova type 1. And I'm going to show you through pictures just how this occurs in our system. First of all, let me say that type 1 supernovas live in our binary system. And what our binary system is a cluster of stars, and you'll have two stars that are simply orbiting each other. So this first picture I'm going to show you basically represents that. And what we're looking at here is essentially two stars that are orbiting each other. They are basically the same size, and just for argument's sake, we'll say that these stars are the size of our sun. Now, in order for a supernova type 1 to occur, there are some things that generally must take place in order for that to happen. Again, we have those two stars that are orbiting each other, and that's kind of what goes on in the binary system. They just kind of orbit around until, well, something happens to interrupt that. Generally what happens is over time the heat that is generated comes about through a nuclear reaction. And it's basically in the core of this. And what happens is it triggers when a higher pressure and temperature within the star's core causes the hydrogen atoms to fuse with helium atoms. So we still have this orbit that's continuously going around, but as you can see now, this star has grown somewhat. And once that happens, once the hydrogen is exhausted in the core actually starts to contract. So what we have is a contraction going on. Basically, you have the energy of gravity that's pressing inward into the star, and you also have gases that are in the center that are pressing outward. So you've got like this pulsating sensation going on, and in the meantime, we still have this orbit that's happening. Okay, so generally after that, what happens is, and I'm going to show you exactly what that means. So here we're looking at gravity. This is gravity just kind of going inward, pushing inward from the atmosphere. Here in the center is the core. And what's happening is the hydrogen is mixing in with the helium, and as it pushes outward, we have heavier elements that are inside the core that are pushing out the lighter elements such as the hydrogen, the helium, and then eventually as they mix, we get oxygen, carbon, but meanwhile we have gravity that's constantly pressing down on this thing. Now, what happens is, after a while, when there is no longer, and what happens is this core turns into more of a iron. Once that iron does not mix, all the nuclear reaction actually stops. And what happens then is the gravity now takes over this mass and this massive star. And since there's no longer anything to push outward, the gravity takes over and condenses this into just an iron ball, basically. And what we're left with is a center or core that has now become a white dwarf. So I'm going to kind of show you what that looks like. So here we have our star that we started with, and now what we're looking at is the result of all the elements that have been blown off, and what remains now is a white dwarf. And that white dwarf has not finished its cycle yet. It has quite a little ways to go before it actually will become something even greater. And we'll talk about that in a few minutes. Now, the red giant's core, which generates, what it does is it generates enough heat to fuse its helium atoms into carbon, as we talked about. The nuclear fusion in turn creates the other elements, and that also includes oxygen and carbon as well. And eventually what happens is the radiation generated within the star's core pushes the outer layers out into the atmosphere. And essentially what we're left with is the red giant. And of course, after it has blown off all of its elements, we're left with that white dwarf. So the star has basically died at this point, and what it's remaining is simply this white dwarf star. All the meanwhile, now remember, we still have, the stars are still orbiting each other. Essentially what happens after that is, in time, the other star, and that would be the other blue star that we were looking at just a minute ago, it becomes a red giant. And as its outer layer expands far from the core, just the same as this star had done in the beginning, becomes less and less dense. And what happens now is it's closer to the white dwarf, and the gaseous materials from the red giant feels the gravitational pull of the white dwarf, and it basically gets sucked in by its neighbor. So you have this, the secondary star that has also reached the red giant stage. And what's happening here is the gravitational pull from the white dwarf is now pulling this energy from the red giant over to itself. And that's kind of what we're looking at here. Now, of course, when that happens, we're going to have a problem. And it's going to be a huge explosion after that. And that's what this is depicting at this time. The white dwarf pulls more and more stellar material into itself. And as a result, when it reaches 1.4 solar masses, and that's about 40% of the mass of our sun. So we're talking about a huge explosion. Fortunately, because the molecules don't have anything in space to bounce off of, we don't actually hear this. But if we could hear it, I would imagine it would probably be ear piercing. But this explosion, what happens is this white dwarf that was here in the beginning, after it has sucked all the energy out of the second red giant, it explodes into this massive explosion. And these explosions are billions, at least 15 billion times the solar mass of our suns. And this is the reason why we can see these explosions from way across the universe. And that's the reason we can see them, is because of that. And so that, of course, aids scientists to be able to study these and determine exactly how far away they are. It also gives scientists the opportunity to see and be able to compare just how much our own universe now is expanding and how fast it is expanding compared to how it was before in another time. Now, you may be asking yourself, well, what happens to the red dwarf that was left here? See, we have this red dwarf. There's still kind of here, but what's left of the red dwarf is simply its core. And after that explosion happens, the atmosphere starts to dissipate, and the core that's left is basically blown into space. So basically we have the explosion that has happened from the white dwarf itself, and it has exploded into the atmosphere, and what it does is it'll just blow this core right into Earth, or right, and not into Earth, but into the atmosphere. And of course the white dwarf is just blown into oblivion, so there's nothing left actually. We just have a dark space where two stars used to orbit. These are very fascinating events that happen. Now, of course, they are rare, but they do happen in our universe. And the importance of this, I can't stress enough, because it does help our scientists to be able to see billions and billions of years ago what our universe looked like, and of course, how much it has expanded up until now. So in other words, the supernova that is 1 billion light years away is as an actual explosion that happened a billion years ago. And its light that's left over gives us a view of the universe as it looked a billion years ago. Now that's quite fascinating, to be able to look back in the history of the expansion of this universe and see exactly what it looked like at that time. So these observations will allow our astronomers to determine how fast the universe is expanding at different times in its history. Now, each dark energy theory, and we have a lot of dark energy theories, because we're able to use these beacons of light as standard candle lights. And I don't mean the candle lights that you put on the table, but actual beacons for our scientists to be able to look for in the atmosphere or in the universe, and be able to determine by measuring the light and the rate of the light. It also will help strengthen and weaken some of the predictions and the ideas that we already have about our expanding universe. So, it's very important to know that, and to be able to measure the the light sources and be able to determine that our universe is expanding quite rapidly. Don't worry, we still have a lot of time left here on Earth, so we don't have to worry ourselves about that. But I hope you've enjoyed this presentation, and I do hope to see you sometime in the near future. But for now, I hope this was very informative to you as it was for me, and I had fun doing it. Thanks, and see you soon. Bye.